Hello folks, today in this video I'd like to talk about periodic motion. We're going to talk about what it is, a mathematical model to take a look and analyze it, and then lastly one specific example of a system that does periodic motion. Let's go ahead and get started. So what periodic motion is any motion that repeats itself in equal intervals of time. It's all based around that idea of a period. The period of any motion is how much time it takes for it to do one cycle. And I think you guys have hopefully heard of period before. So if you're looking at these graphs here, the period of this first bit of motion there is from when it starts there, the x-axis, and completes one full cycle, both up and down. Now, there are lots of different examples, as you can imagine, of things in our world that do periodic motion. Anything that's like spinning or going in a circle, or something that's like a wave, like sound or light. All of these things do periodic motion because they repeat after fixed intervals of time. That time, by the way, period, is typically measured in seconds. So you'll see sometimes minutes or hours creep into problems sometimes. Now, this can take many forms. I've given you a bunch of graphs here to take a look at that are kind of interesting, but we're going to kind of restrict ourselves with graph A, which is called simple harmonic motion. Simple being that it's fairly easy to mathematically model. We can mathematically model it using trig functions, which makes the math a bunch easier. So let's go ahead and take a look then at what is that mathematical model here. So our mathematical model is all based off of, let me get my mouse working here, just sines and cosines. So to do sines and cosines, here we see that we have a position function. We say that the position of some particle in periodic motion at time t is equal to a cosine of omega t plus phi. Let's kind of break this one down a little bit. So A, you've probably heard of before. It's the amplitude of the motion. Amplitude is just the distance of the maximum displacement from the center line or wherever the motion is at its start. How far does the particle go up, or how far does it go down? So looking at this graph over here, I'll label it in red. This distance here is your amplitude. This one would also be the amplitude, because that's how far below the x-axis that it goes. So that's where its max and its min are going to be. Now you'll notice that this particle oscillates back and forth between the maximum and the minimum, and that's not an accident. That's because this cosine function has an interesting piece to it. If you remember from trigonometry, the maximum value that the cosine can have is 1, and the minimum value the cosine can have is -1. And so because it's a times cosine, that will oscillate back and forth between 1 times a, or the maximum value, and -1 times a, which is that minimum value. And so that cosine is what produces this periodic motion. And then the stuff in the inside of the cosine is just telling us how fast is this motion wiggling. What is its frequency there? And so we're going to talk about that first one there, angular frequency. You guys have probably heard of frequency before, just normal frequency. That's this right here, frequency, and it's the inverse of period. You know, period's the time it takes for it to do one cycle, while frequency is the time or the number of cycles it goes in one period. So frequency is the cycles per second, how many times it waves per second. And so that's the unit of frequency as well, cycles per second, which we also define as a hertz, or sometimes you'll see it written as just seconds to the minus first. Now, this isn't frequency, but angular frequency. And the reason behind that is, well, I'm putting it into a trig function. And so my argument has to be an angle. So I need to turn frequency into some type of an angle. And the way we do that is we think about a circle. If you have something going in a circle, if it completes an entire cycle of its motion, what angle has it gone through? Well, it's gone through an entire circle, and the entire circle has 2 pi radians as the angle. So we're going to use radians here. And so we would say that the angular frequency is simply 2 pi times normal frequency. So if frequency is inverse seconds or 1/seconds, angular frequency is typically measured in radians per second. So it's that many angle, that much angle, that many radians every single second. So you can kind of think of like a speed in a similarity, how many angle or how much of an angle it's going through per time there. And then lastly, you've got phase constant. What this phase constant thing does is it actually shifts your graph left or right, because you'll notice it's starting right up here, I'm going to clear my screen here. I'm starting right up here at x equals 0, or t equals 0, right at the maximum. The reason that's happening is, let's consider, for this one, I always like to consider t equals 0. If t equals 0, then it's just the cosine of phi. If phi was 0, that would mean that I would be taking the cosine of 0. And the cosine of 0 is 1. That's why I'm starting off at the maximum, because a times 1 just gives me that particular maximum value. So this is occurring when there is a phi of 0. But I wouldn't have to start my motion there. If I had a particle that was starting off right at the midpoint, it might have a different thing I need to put in the cosine to get it to start there. And so we can see, you can kind of imagine that you could put in any number and then make it make this graph start at whatever point you would like. We typically think of shifts in like whole numbers of pi, typically, because if a whole circle is 2 pi radians, we're going to mostly consider, pi over 2 or pi or 3 pi over 2 shifts left or right. Let's consider, for example, what would happen if I wanted to do a phase angle. I'll do this one in red of pi over 2. Well, if you started off at pi over at t equals 0 still, I always think that's the best way to think about it. So that's 0. I'm taking the cosine of pi over 2. And if you remember back from your trig class, the cosine of pi over 2 is 0. So that one would start me off right there. And then after pi over 2, the cosine actually becomes negative. And so that's what produces these negative values here. And so it would go down something like this. Once you got to here, though, then it would come back up and go like that. And what you would notice is that it looks like my graph has just been shifted over to the left. And I can tell that because that's a positive phi value, or a positive phase constant. In general, a positive will shift it left, and a negative will shift it right. Okay, let's go ahead and actually take a look then at some examples of these values here. So I've got 3 curves here to take a look at. Sorry for the image being a little fuzzy there, but go ahead, take a second, pause the video if you need to, rank the following curves here for these 3 experiments, 1, 2, and 3, based on their angular frequency, amplitude, and their phase. Okay, so way I take a look, let's do angular frequency first. I'm going to go from smallest to largest here. And if I'm going from smallest to largest, it looks like the one with the smallest frequency, the one that's taking the slowest amount of wiggles, is definitely 2, right? Because 2 definitely takes its time. It's not oscillating back and forth very fast. Then if I'm going between 3 and 1, 3 being the yellow curve and 1 being the blue curve, from what it actually looks like those are oscillating back and forth at about the same rate. Take them at the same number of cycles in the same amount of time. So I'm going to say 1 and 3 have the same angular frequency. Looks like that to me here. Amplitude, that's how far it's being displaced from the middle point. It looks like, again, 2 definitely has our lowest amplitude there because it doesn't have very high of a peak there. And then it looks like the yellow one, 3, is up next. And then finally, number 1 clearly definitely has our largest amplitude there. Then we get to the phase one. So I brought in phase just to kind of get us thinking here, though I'm going to introduce a fun little wrinkle that phase is difficult to rank from highest to lowest. And we'll get to that in a second here. But it says, assume that 0 phase angle is when cosine of omega t plus phi equals 1. So if I'm looking at t equals 0, so I can ignore this part here. If I want it to be 1, I would need a phi of 0. And so it looks like the only one that has its maximum there is the yellow curve. So I could say that 3 occurs at phi equals 0. That seems pretty standard there. Then I'm looking at the green one and the blue one. And like I had said on the previous slide, if you advance to the left, it looks like you have a positive phi value. And if you advance to the right, it looks like you have a negative phi value. So if I'm looking at that yellow one, the green one definitely looks like it's shifted to the left there, right? I can see that it's kind of shifted there. Now, it's hard to tell exactly how much it's shifted. In fact, it might be like pi over 4 shifted perhaps. But I wouldn't ask you to estimate that granularly on a thing like on a problem like this, we'll just say that shift number 2, phi, it's definitely got a positive value of phi because it's shifted to the left there. And then number 1, I would say that's actually looks like it shifted to the right there, right? Just going over that way. And we had said that for shifting to the right, you would need a negative phi value. Again, probably shifted the same amount as the green one because it looks like they meet right there in the middle at t equals 0 there. Now, you might have already figured out the wrinkle. And the wrinkle is I'm being pretty generous when I say, oh, this one's clearly shifted to the left, because you could totally have a different perspective than I did and say, wait a second, Baker, like if I just think about this green one differently, I could argue that it was shifted from, here to there. That looks like it shifted to the right. And you would be totally correct. And that's because that's the way angles work, right? Pi over 2 positive is the same thing as negative 3 pi over 2. So we have to be careful. I will tell you, if you ever, on anything I do, put just a complementary angle like that, you are, I'm not exactly sure the math term there, but you're absolutely fine. No problem there. These things definitely rotate. And in general, I try to always go for the smallest angle. That's why I picked pi over 2 rather than the negative 3 pi over 2, just because it's a little easier to visualize on a graph. But you would be right that you could technically pick either way, and there's no clear way to know which one's correct because they're both correct. So I picked the smallest one in general. Okay, let's head on and take a look at, besides position, could I think about other variables when it comes to periodic motion? And the answer is definitely yes. But before we do that, let's take a look at some graphing practice, because one skill you do want to have is to be able to actually sketch or graph these curves. So this first one says, draw a graph of position versus time with an amplitude of 2 meters, period of 4 seconds, and a phase of 0. So I've always been defining phase to mean that a phase of 0 is, okay, it starts at its maximum. Again, I'm fine if you pick another one to be your 0. It's just a purely arbitrary thing. It just would change the trig function that you're using. But I'm going to go ahead and start off with phase of 0, meaning it's at its maximum, and its maximum would be 2. So we're going to go ahead and start at t equals 0 at 2 there. And then I know I need to have a period of 4, which means I need to repeat after 4 seconds, which means I need to be back at 2 at 4 seconds. My tip when you're drawing is to always try to find the midpoint as well. Where's the half point? At the half point, at 2 seconds, it should be at -2, right? Because that would be the full range of motion there. It looks like this x-axis or y-axis is a little off, but that's okay. And then from there, just kind of sketch your curve. I know it's going to go down and up and down. Now, I am definitely not drawing your artistic skills. My artistic skills are terrible, but as long as you have the general gist of how this curve is supposed to look, you've got the right answer there. This next question just asks us to consider the same period and phase we did in the first one, but with half the amplitude. So what would having the amplitude do to a wave? Well, that'll just make the wave kind of squish down more toward the x-axis here. And so we'll kind of draw a wave here that is a little squished from there. And then our last problem to take a look at is what would we do if we had to do the same one as the first one, but now with a phase of pi over 2? Well, it might be helpful. I'll go ahead and redraw the first wave that we did. So that was that one there. And then I'm going to draw the one with the phase of 2 in blue. So to do that, for phase of pi over 2, that's a full 1/4 of the way shift. So if I'm thinking here, whatever would be at 1 would now be at 0. So that's actually right at 0 amplitude there. Phase of pi over 2 shifts at 1/4 of the wave. By the way, that's just simply because pi over 2 is 2 pi over 4. So 1/4 of the motion. And then what we'll do, we'll just kind of redraw our curve here. Should come back up to the x-axis at 2, up 2, and then there. And so you can see, yeah, I've been shifted to the left because it's a positive value of phi, and I've been shifted to the left 1/4 of the wave's motion. Okay, so now we're going to actually take a look at those other variables, right? We've been dealing with position, how far it's been displaced from its midpoint, but could you consider other variables as well? And the answer is absolutely you could. So we're going to talk about velocity and acceleration here. So if you want to think about velocity and acceleration, you might want to think about the relationship between distance and velocity and acceleration. You might recall that if you had like a position versus time graph and you wanted to find the velocity of that graph, you would just take the slope of this line, right? And in a similar way, to find our velocity, we want to take the slope of the position thing. Now, if you've taken any calculus, which you do not need to know for this class, you might recall that taking a slope is taking the derivative of a function. And if our position graph was a cosine function, then taking the derivative of cosine is a sine function. And so our velocity and acceleration curves will look very similar in terms of the way they're built to the position one. They'll just use different trig functions. So velocity, it looks like here, is negative a omega, omega being the angular frequency, times the sine of omega t plus phi, just like we saw with our position function there. So a few things to note. There is a negative sign out here. So what that means is that it has like the opposite direction thing to the position function. And then lastly, it also is on a sine curve, not a cosine curve. And remember that sine and cosines are kind of opposite in a way. So if you're looking up here at this graph, and it's a little hard to see sometimes, so you could even take a ruler out and kind of put a straight edge up there. But if you look here, when my distance is at a maximum, when I'm at that maximum distance, if you were to drop a line down, you should notice that the velocity is at a minimum. It's at zero. And that actually makes a lot of sense. If you have some particle oscillating back and forth and back and forth, when it reaches this amplitude, it has to turn around. And so that's where it briefly stops just for a second. And so your velocity, so v equals 0 at the maximum position or displacement, maximum displacement there. Now, velocity also has a maximum as well. And that maximum, it makes sense, is the thing in front of this sine function. We've already talked about how sine and cosine go from 1 to -1. So this is going to be the maximum value for that v. And that maximum occurs, you'll notice here's a max, occurs when the position is 0. So they are in some ways opposites, that velocity is maximum when the position is 0, and velocity is at 0 when the position is at maximum there. As you can imagine, acceleration works very similarly. If I continue these lines down, you'll see that acceleration has its, we'll say maximum because it's just the negative is just a direction symbol, but it has its maximum when displacement is a maximum. So it's at max displacement. That's an at symbol. And it has acceleration equals 0 at x equals 0. So it follows the same as the displacement, which makes sense because it is also a cosine function. And then if you know any calculus, you'll kind of see what's happening here is I'm pulling out this omega every time, one more omega. So x, the x of t function, has just a cosine omega t plus phi. And then for velocity, there's 1 omega pulled out. And then for acceleration, there's 2 omega, so omega squared there. But that just changes the amplitude, the amount of this maximum for the velocity or the acceleration. Okay, let's take a look at a couple of problems here. So it says a particle in a spring has a motion that produces this graph. At what time does this particle have the greatest speed? At what time does this particle have the greatest acceleration? What is this particle's angular frequency? What's the particle's maximum speed? And what is its maximum acceleration? Take a second if you want, pause the video, take a look and see what you think of that. Okay, so let's just do the time thing first. So remember, this is a displacement graph. So this right here is x of t. It's telling me how this particle is functioning with time. So remember that when you have your greatest speed, that's going to be when the position is at 0. So this is going to have its greatest speed anytime this crosses the x-axis. So that looks like 0, 2, 4, and 6. It's going to have its greatest acceleration then at the same time that position has its greatest maximums. So we're going to say, looks like 1, 3, 5, and 7. Okay, what is the particle's angular frequency? So remember, angular frequency is our omega, and that's 2 pi times f, which is the normal frequency, or it is 2 pi divided by t, and t is probably a little easier to get here. T is your period, how long it takes for it to repeat, and it looks like to me the period here is 4 seconds, and so my omega then would just be 2 pi divided by 4 seconds. I'm fine if you want to leave this as a particular, like a multiple of pi. So that's pi over 2 radians per second. Or if you want to actually punch it in your calculator and actually get a number for pi over 2, which I guess I could just know off the top of my head. Yeah, that makes sense. It's about 1.57 radians per second there. For the maximum speed, remember that Vmax is amplitude times omega. And so I just got to find the amplitude of this, which it looks like it goes up to 0.5 meters. And then my omega was that 1.57 radians per second. And so it'll just be 0.5 times that. And sorry, it's getting a little messy here, 0.785. Now my units for Vmax then are going to be meters per second, because now I'm talking about a velocity. Radians is a weird kind of pseudo unit. So I put the radians in here for omega, but we're not going to continue using radians after that. So that'll just be meters per second. Then lastly, for acceleration, remember that Amax is a omega squared. And so a very similar calculation to what we just did. We're going to do 0.5 meters times 1.57 radians per second squared. So I'll do 0.5 times 1.57 squared, and I get 1.23 meters per second squared. Okay, that's been a quick intro to periodic motion. In our next video, we'll talk about some specific examples and take a look and see how it works. Thank you so much for watching. Have a great rest of your day.